Alright, so in this lecture we're going to start a new topic, electric flux and Gauss's law. Okay, so electric flux, it's also a new concept to a lot of people. Okay, again, it's a defined quantity in physics. Why do we define it? Well, because it's useful, right? And we can see why it's useful. And then it can also help us find out the Gauss's law, which is alternative to Coulomb's law, and we're going to see the significance of Gauss's law in a little bit. Okay, but first let's define this thing. Okay, take a look at the first slide, PowerPoint 4. Okay, so imagine there's an electric field in a region, right? There's an electric field here. Okay, you don't see that, and it exists, right? Let's think about microwaves. Okay. Microwaves, that's because E&M fields are oscillating. That's how you get microwaves. So the electric field is in a region. Okay, if there's a surface there, okay, you can define a thing as the integral of the electric field on this surface. Okay, so that's how we define electric flux. It's totally mathematical definition. Okay, you can't find an everyday equivalent to this. Okay, it's totally mathematical. Okay, so maybe again, when you learn a new concept in physics, it may take you some time to get used to it. Okay, so just practice and practice, you can get more familiar with that. So this guy is defined as the integral of this electric field on the surface. Okay, and then this is a dot product, E dot dA. So if you want to evaluate this integral, this is always going to, first of all, you should use the definition of the dot product, if you still remember that. That's going to be the product of the magnitude of these two vectors times cosine theta, which is the angle between them. Okay, that's the definition of electric flux. We use the symbol phi. This is a Greek letter, phi. For electric flux, we usually put a subscript E here because we're going to define magnetic flux later. Okay, so the unit, it's going to be newtons meter squared over coulomb, which is going to be the product of these two units. Okay, all right. So and then take a look at this dot product, right? So there are two vectors. E is the vector. E is the electric field, right? We know that. We learned that. What is the direction of dA, right? First of all, dA is gonna be the infinite small area, right? So it's infinite small area element. Okay, like this dl, dx, dq we have discussed. How come that thing has a direction? Well, it doesn't. Right, it doesn't. But in order to make a dot product, we have to make this guy a vector. Again, you can define anything you like in physics. Okay, the only matter is that if you can make a consistent or complete theory out of it. So we have to define this dA as a vector. So the magnitude is just going to be the magnitude of this the small area. Okay, it's going to be a very small number. Okay, that's fine, but it still has a magnitude. What is the direction? Okay, so the direction is not that intuitive. Okay, the direction is defined as the normal vector perpendicular to the surface. Okay, so if this is the surface I'm talking about, right? You pick any surface. You pick a very small, infinitesimal area here. What is the direction of this dA we define in this part? Okay, is a definition. Okay, is this. Okay, perpendicular normal vector. Okay, this is not that intuitive. Okay, but that's a definition, and all the physicists just found that this is the best definition. Okay, so this is the direction of this dA. Okay, and then of course, if there's an electric field in this region, the E has a direction in any direction, right? So this E vector is going to have an angle with this normal vector, right? So that's the angle theta you put in this equation. If you want to evaluate the flux through an area in an electric field, that's how you do that, right? That's a definition. Okay, that's a definition. You can always define anything in physics. It may not have a everyday equivalent. You may not need to use that in your life, okay? But in this theory, It's very important and useful definition, okay? So you should be careful. A lot of people, they would pick the theta angle between this electric field and this surface. For example, if I have an electric field in this direction, okay, a lot of people, they would pick the theta angle as this, and then the surface, they would pick this angle, okay? So let me do this. If there's an electric field in this direction, okay, if there's an electric field in this direction, the angle theta you pick is going to be, if I want to calculate electric flux through this area, the angle you pick should be the angle between this electric field and this normal vector. So this angle, okay? Not this angle. Some people, they would pick this. They think this is more intuitive, okay? The angle between the electric field and the surface, okay? Why isn't this angle? Okay, no, that's not the definition. The definition is this angle. The normal vector and the electric field. That's the definition, okay? So you would say, why don't we, this is not that intuitive. Why don't we define the angle between this and the surface? Okay, because you don't always have a flat surface, okay? If you have a spherical surface, okay, if you have a spherical surface, okay, say, okay, I can use this, okay, this is handy. If you have a surface like this, okay, and you want to define this, there's an electric field, you want to define the angle between the electric field and the surface, then what is the angle you pick, right? Because you can, what is the angle between this and the surface? This is not a flat surface, right? You can draw an angle this way, and this way, and that way, and that way, and that way, right? So it's not unique. But if I define the angle as the normal vector perpendicular to the surface, so if I want to find an angle between this vector and this spherical surface at this top, there's only one direction of this dA I define, perpendicular, straight up, unique, right? So if you define it as tangent, it can be going this way, that way, that way, that way, that way, if it's not a flat surface, okay? So if you define it as a normal vector, it's unique. The direction is going to be unique, and the angle between the electric field and this surface is going to be unique, okay? So that's the reason, okay? Even though it's not that intuitive, okay? We define the angle, the direction of this dA vector perpendicular to the surface, not parallel, not tangent to the surface, because we want this direction to be unique, this angle to be unique. That's the reason, okay? Think about a spherical surface. If you pick the tangent as the direction of the dA, you can't find a unique vector, you can't find a unique direction, unique angle, okay? So you can sort of think of, you can think of electric flux as proportional to the number of electric field lines passing through the surface, okay? So take a look at the image on this, on the first slide, okay? You can see that if there's a lot of electric field lines through the surface, that means the electric field is very strong, right? And then at the end, if you integrate the electric field on this surface, you will get a large number. If there's only like 3 or 2 electric field lines passing through the surface, the electric field in that region is going to be very weak. So you would just get a very small number, right? So I hope that can help you sort of visualize electric flux. Again, it's totally concept, it's totally mathematical concept. It doesn't have any everyday equivalent, okay? So you can sort of think of it as proportion to the number of electric field lines passing through the surface. Or you can think of it just as the electric field lines passing through a surface, right? If there are a lot of lines passing through a surface, it has a lot of flux. If there's no lines passing through the surface, zero flux, right? If there's a very few electric field lines passing through the surface, okay, very small electric flux, okay? So I hope that can help you understand and visualize electric flux. This is a totally mathematical concept. So even though this definition is defined using integral, in this class, we never need to evaluate any integral using this definition. Okay, so don't be scared by this. A lot of people in this part, when they see this integral, they're scared by that. Okay, they don't know what to do with that. In this class, intro-level class, we're not going to really integrate anything using this definition. We're just going to take a look at some special cases. It's just going to become algebra, okay? So take a look at the slide, the second slide. These are the special cases we're going to discuss in this class. First of all, if the electric field is perpendicular, totally perpendicular to the surface everywhere, and the electric field is a constant, okay? So it's a uniform electric field passing through a surface totally perpendicular to the electric field. So like this, right, the first image. So you have a surface and then totally perpendicular to the electric field. So the electric field says to the right, uniform electric field. And then you have a surface like this, okay? So the surface like this, okay, perpendicular to the board. So that's going to be perpendicular to the electric field, right? So the electric field is going to the right. I have a surface this way. So all the electric field lines are perpendicular to the surface, okay? In this case, how do I use the definition to find the flux? It's very easy, okay? So all you need to do, start with the definition, okay? It's going to be E dot dA, and this is a dot product. There are two symbols, okay? It doesn't matter how weird these two symbols are. There are two vectors. Let's use the definition. E, the first vector, the second vector, cosine theta, okay? Now let's see. E is a constant, right? Because this is uniform electric field. So that means this is going to be a number. It's not going to be a function. It doesn't depend on where the point you pick, where this element you pick. So this E, you can actually take it out. Now what about cosine theta? Remember, the cosine theta is defined as the angle between these two vectors, right? If you have vector A dot vector B, you always get the magnitude of A times the magnitude of B, cosine theta, the angle theta between these two vectors. So you're going to draw the direction of this E, draw the direction of dA, and then to find the angle between them, okay? E is in this direction, and it's uniform, so it's the same everywhere. Now what about dA? Well, you're going to pick very, very small, infinitely small element on this surface, right? Say I pick this element, very small, okay? Now what is a dA? How do you draw dA? Remember, the definition of dA is perpendicular, a normal vector perpendicular to this dA you pick, okay? So if this is a surface, you pick a dA here, very small. What is the direction of this dA? You actually draw a vector that way. That's the definition. That's the definition. That's how all the physicists agreed to define it. Okay, even though it's not that intuitive, that's the definition everyone agreed on. So everyone should use that definition. Okay, and that's the best definition. Okay, so that's why all the physicists agreed that let's use that definition. Okay, so that's actually the dA you should draw. Okay. So the angle between the E and dA, what is the angle between them? 0, because they are in the same direction. If they're in the same direction, the angle is going to be 0, right? So if the angle is 0, then this cosine 0 is going to be 1. Okay, that's nice, okay? But you should see that if this is a cosine theta angle can change. If you pick, remember, you're going to integrate dA, so that means you're going to pick a dA here, here, here. So actually, you're just adding all these contributions, right? But if this is a flat surface, totally perpendicular to the electric field everywhere, the dA you pick is always going to be in that direction, right? So you have a surface totally perpendicular to the electric field to the right. You pick a dA here, 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 here. What is the direction of this dA you should draw? Perpendicular, perpendicular, perpendicular. Okay? So that means the dA you draw is going to be in the same direction of the electric field everywhere on this surface. So this cosine theta is not a variable, right? It's going to be a constant. It's always going to be 0 degree, 0 degree, 0 degree, right? So that means I can also take this out. Right? And cosine 0 is 1. okay? Cosine 0 is 1. So in this case, you will just get e times the integral of dA. And then we have seen this before, right? If there's no function here, you just integrate this small element. You're just adding all these small elements together, right? There's no function. If you add all these small dA's together on this surface, what do you get? You just get the total area, right? So that's just going to give you E times A. Okay? So that's the conclusion if you have the simplest case. Electric field uniform in one direction, and then you have a surface totally perpendicular to the electric field. So the surface is totally perpendicular to the field. Doesn't mean the angle is 90 degrees. Again, you see, a lot of people, they will make that mistake. This is a little bit confusing. I know that because this is not intuitive, okay? Because when we use the theta angle, we are not using the angle between the electric field and the surface, right? Actually, you can only say there's angle between them if the surface is flat, right? If it's not flat, you can't find a unique angle between the vector and the surface. In this case, this is a flat surface. A lot of people would say, oh, the theta angle is 90 degrees. This is the angle between the surface and this, right? But the dA we define is in that direction. So the angle you should use between E and dA, when you do this, when you evaluate this integral, it's going to be 0. Right? If you use cosine 90, you actually get a 0 at the end, which doesn't make sense, right? Because we said that you can think of the electric flux proportional to the electric field lines passing through the surface, right? There is a lot of lines passing through the surface. You shouldn't get a 0, right? You should get to some number, okay? So if the surface is perpendicular to the electric field, it's going to make the angle between E and dA 0 everywhere, okay? So you will get E times A, okay? So this is the shortcut. This is a conclusion we can remember. I usually don't recommend remembering all these shortcuts and conclusions, but this is going to be a very useful conclusion we can remember. So every time I see an electric field perpendicular to a surface everywhere, okay, so we're going to see a case that where even the surface is not flat, right? It's spherical, but if the electric field is perpendicular to the surface everywhere, the answer I get at the end is always going to be E times A, okay? So this is a very useful shortcut, useful conclusion we can remember. So instead of doing this integral, or you can repeat this, you can do this, right? Actually, you're not doing any integral, right? You're not integrating anything. There's no function here. You pretty much take out everything else except this dA here, and you integrate dA. You don't even need the integral table. It's going to be A. Okay, so this is something I can remember and as I said, we're only going to be looking at these special cases in this class. We're never going to really integrate anything using this definition. Okay, we're never going to integrate anything in this flux part. Okay, so that's the first special case. When the electric field is perpendicular to the surface everywhere, okay, the flux, E times A. That's it. Okay. Now, what about the second one? The second one is this. If I have a surface parallel to the electric field, okay, the electric field, say, is still to the right, uniform, okay, uniform to the right. Now, I place a surface this way, right, like, or this surface, right. Electric field is to the right, I place a surface parallel to the electric field lines. What is the electric flux through this surface? How do I calculate the electric flux? Use this definition, right? So I will still have, okay, E dot dA, that's going to be equal to E dA cosine theta. Okay, E, take it out, because E is going to be a number, right? Because you tell me this is a constant uniform electric field. What about cosine theta angle? Again, you shouldn't say 0, right? A lot of people will say, oh, they're parallel, the angle is 0. We need the angle between E and this dA we define. How did we define the angle of dA? Perpendicular to the surface. So in this case, if you want to draw dA, you should draw it this way. I pick a very small element here. what is the direction of dA? This way, right? This is the direction of dA. So if you have a surface like this, the dA you should draw is going to be perpendicular, okay? And you need this theta angle between this vector and this electric field vector. What is that angle? 90 degrees. In this case, it's 90 degrees, okay? So, and then it's going to be 90 degrees everywhere, right? Because you pick a small element here, that's the dA you draw. A small element here, that's the dA you draw. You will get 90 everywhere. So the cosine theta is not going to be a variable, it's going to be a constant. In this very special case, take it out. E cosine 90 dA. Now I don't even need to do anything more, right? Cosine 90 is going to be 0. Whatever multiplied by 0 is going to be 0. Okay? So that's another special case we can remember. If the surface is parallel to the electric field everywhere, that means the electric flux through the surface is going to be 0. It also agrees with the fact I just told you. You can think of the flux as the electric field lines passing through the surface, right? If the lines are parallel, all these lines are going that way. There's no single line passing through, crossing this surface. So there's no flux, right? All the lines are parallel to it, okay? So of course, the electric flux you calculate, it's going to be 0. So these are the two special cases, okay? And then of course, if you have the flat surface, which makes an angle with the electric field, but it's not 0 or 90, in that case, you will get the third case, right? You have an electric field to the right, say still to the right. Now you place a surface this way. Okay? So you have the electric field that way, you place the surface this way. Now in this case, how would you draw the dA, right? So you're going to draw the dA perpendicular to the surface, right? So in this case, you still pick an electric field this way. No, you still pick a small element. This is going to be the dA you draw. This is going to be the dA you draw. Right? So what is the direction? What is the theta angle you use? You should use this theta angle. Okay? And then if you repeat what we just did, you will still get the E dot dA, and then you will get E dA cosine theta. Now E and theta, they're going to be constant, even though you don't have a 0 or 90 degrees. But these two guys, this is going to be two numbers everywhere. You can take them out. You get an integral of this dA, no function in it. That's just going to give you the total area. So you're just going to get E cosine theta times A, or EA times cosine theta, right? So that's going to be this special case. So when the surface does make an angle with the electric field, okay, you just do EA cosine theta, okay? So you still don't need to evaluate any integral, okay? So these are the only three special cases we're going to discuss in this class. So don't be scared by this integral in this part. We never need to integrate anything in electric flux. We never do, okay? So, okay, but even if you define that the electric field, the electric flux as the angle between this E and dA, there's still some ambiguity here, because if this is a surface, you tell me the surface, the electric field, the flux, the dA is defined as perpendicular. There's still two options, right? I showed you that this should be the direction, but this is nothing wrong. There's nothing wrong if I say this is also the direction of dA, right? So for an open surface, or for any surface, right? You can actually, even if you tell me that our definition is perpendicular, I draw a normal vector perpendicular to the surface, I still have two options to draw that. And that's still going to make this theta angle different, right? For example, if I still have the electric field going in this way, okay? If I have this surface here, I draw a vector up, it's going to make a small angle. I draw a vector down, it's going to make a large angle. And this cosine theta is actually going to make it different, right? It's going to make it positive or negative. So there's still some ambiguity here. So in order to remove that, let's adopt another convention, because it's totally definition, right? So for any open surface, we're going to always make the flux positive. So that means if there's an open surface, I want to calculate flux. This is electric field, so I should pick the up as the dA, not the down, because I don't want to make it negative. So for open surface, the convention is easy. You always make sure it's positive, okay, when you calculate the flux. For closed surface, then it can be positive or negative. We always pick the outward direction for dA, okay, to remove the ambiguity, right? So for this guy, if this is a surface, there's electric field in this region, how do I define dA, right? I can say perpendicular, either this direction, outward, or inward, right? Inward is also perpendicular. So there's still two options, okay? So our convention is this. Let's just remove this inward. Let's just say the dA is always outward, okay? So that everyone agrees on that. So when we talk about the closed surface, we know that the dA we draw is going to be always outward, 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 right? You never draw a dA inward. Okay, so that can also remove that ambiguity, okay? So for a closed surface, the flux can be either positive or negative, okay? And in this class, we're going to be dealing with closed surface most of the time, okay? So you just always draw a dA outward, perpendicular to the surface, okay? So that's the flux. Now let's take a look at the example, okay? So that's the example in slide 4, PowerPoint 4. So I want you to calculate the total flux through this cube. If there's an electric field in x direction, positive x direction, okay, and the cube is sitting on this x, y plane, okay? So now let's see. Again, we're just going to use the definition, but it's always going to be one of these three special cases. We never need to integrate anything, okay? So the electric field says in the x direction, so let's draw it out. Okay, I don't think I need this, so I'm going to erase this. So, electric field is to the right, okay? Uniform, okay? In the x direction. Now there's a cube here. No, this is y, this is z, but it doesn't matter. All right, so I think that's how you draw a cube in 3 dimensions, okay? Now we want to calculate the flux through this whole cube, right? So all you need to do, because this cube has 6 surfaces, so all you need to do is just calculate the flux through each surface using the definition, and then just add them together, right? So you would have a flux 1, the top one, right? Flux 2, the bottom one, bottom surface, right? Flux 3, the front surface. Flux 4, the back surface, right? And flux 5, the left surface. And flux 6, the right surface. And then you just add these 6 numbers together, right? That's how do I find the flux through this whole cube, okay? Now let's see. Again, as I said, we're just going to use this conclusions we drew for these special cases. We don't need to evaluate anything. Now let's take a look at the top surface, okay? Because at the end, the total flux is just going to be flux 1 plus flux 2, 3, 4, 5, 6. Now let's see, the top one, okay? So which case is the top one, right? Perpendicular, parallel, or has an angle? Think about this, right? If this is a cube, okay? Now the electric field is to the right, okay? So that means this is totally parallel to the electric field, right? Electric field going that way, this is the top, okay? So I don't need to calculate that. It's going to be this case, right? Electric field parallel to the surface. What is the flux through the top surface? 0, right? 0. Because there's nothing passing through the top surface, right? You get a 0, okay? What about the bottom? Bottom is that surface. What do you get? Still parallel to the electric field. It's going to make the flux 0. And there's no line passing through the surface. It's still going to be that case. 0. Now the front one, this one, okay? This one you're looking at. Electric field is going this way, this way. There's a lot of electric field going to the right. What is the relation between them? Parallel. The surface is still parallel to all these electric field lines, all these electric field lines. What is the flux through this surface? The front surface, still 0. Still that case. What about the back one? Well, the same, right? This guy still parallel to all these electric field lines. All these electric field lines. No single line passes through this surface. 0. Now the left and right, so the only thing you need, so these two surfaces, there is a flux, right? Because you see, there is a electric field lines passing through the surface, right? You do need to calculate them. So the only thing you need to calculate is going to be these two numbers. So there are 4 zeros together, right? You only need to calculate the 5th and the 6th, and then add them together. Now let's take a look at this guy, okay? Now take a look at this guy. So I would draw the dA in which direction? This is a closed surface. A cube is a closed surface, right? So it's gonna be outward. So you should draw dA this way. So for this surface, you should draw dA this way, right? What about the right surface? You're gonna draw the dA outward in that direction. What is the direction of E? To the right, right? So so that's going to be the first case. Perpendicular. Perpendicular. So perpendicular, you can take out everything. You're going to get E times cosine an angle times dA, right? But in this case, you see that this is exactly the right surface, right? dA in that direction, E in that direction. So you will get E times A, right? And of course the A is going to be this area of the right surface. Now what about the left surface? Well, you're going to repeat everything. You're going to repeat everything. But the angle you find is going to be the angle between this dA and the E. What is the angle between the dA and the E in this case? E is to the right, dA to the left. So that means you will have angle 180, right? So the only difference is this, right? You will get E cosine 180 times this integral of dA, right? So you will get this. And again, you integrate dA, you don't have any function here. That's gonna be A. So, and this is gonna be negative 1. So you get negative E times A. And this is the surface of the right, the area of the right surface. But these two surfaces, they have the same area, right? The left one, the right one. It's a cube, so every surface has the same area, okay? So that means this guy is just going to be negative EA. I only have one A here, right? Now you put everything together, what do you get? You actually get a 0, right? I don't even need to put numbers in because everything is going to be cancelled, right? There are 4 zeros here. These two guys, they carry negative sign. They carry opposite signs, right? So I don't even need to put numbers in. The final answer is going to be 0, okay? So that's going to be the flux. Now, next time we're gonna, and this is actually a very special conclusion of Gauss's law, which we're gonna discuss next time.